Right now, every piece of you should be light. Not a person, not a body, not a single thought. Just a faint glow spreading through an empty sky. That was the plan. In the first instant of the universe, matter and its mirror opposite were made in almost perfect pairs, and pairs like that cancel each other out the moment they touch and leave nothing behind but radiation. By every rule we know, that is how this should have ended. A flash of light, then a cold, smooth nothing with no one in it. And yet, here you are, wrapped in a body that refuses to vanish. Something tipped the balance. Something let a sliver of matter outlast its opposite when it had no right to. And that sliver became galaxies and planets and the warmth of your own hands. We still cannot say what did it, but the scene of it is not hidden. It is printed across the entire sky in light older than the first atom. And that ancient light is where we start looking. Every time we look hard at why there is anyone here, we find the same shape. A law bending toward emptiness. A universe with every reason to finish the job. And then a gap, no wider than a rounding error, where it did not. It happened with the handful of matter that should have cancelled to nothing. It happened again with a beginning so orderly that nothing in the laws accounts for it. And again with empty space, which by our own arithmetic should have shredded everything before the first atom could form. Different laws, different corners of physics with nothing to do with each other, and not one of them has ever been explained. So this is not philosophy, though it wears the clothes. Why is there something instead of nothing? Why does a universe whose every law bends toward emptiness still carry the one thing it forbids, which is you? That question has hard evidence under it and real numbers, running back 13.8 billion years to the first moment. And the closer anyone looks, the less sense the answer makes. And it is not a story about the deep past either. Whatever cleared out the early sky is still working. Thousands of times a day, in your own muscles, a piece of matter meets its opposite and the pair of them stop existing. You have never felt one. Nobody arranged it, nobody can switch it off, and we will come back for the count. First though, the thing itself. The early universe made it in staggering amounts, and then erased almost all of it. Every particle that makes you has an opposite, a twin built to cancel it out. For the electrons in your body, there is an anti-electron, identical in every way but carrying the reverse electric charge. For the protons, an anti-proton. Physicists call this whole family antimatter, and it is not science fiction. It is a plain consequence of the same equations that describe everything else. The trouble begins with what happens when a particle finally meets its twin. They do not bounce apart, they do not merge, they cancel entirely, and their whole mass turns into a burst of pure light. It is the most efficient reaction physics knows, and nothing else comes close. The rule behind it is Einstein's most famous line, E equals mc squared, written in 1905. Mass and energy are two forms of the same thing, and the conversion runs through the speed of light squared, which is why even a pinch of mass, converted completely, unleashes a staggering amount of energy. Matter meeting antimatter is that conversion taken to its limit. Nothing is left behind but light. None of this asks for faith. Antimatter is manufactured and measured every single day, in physics laboratories and in hospital scanners alike. What nobody can fully explain is why the young universe did not simply use it to cancel itself back down to darkness. It very nearly did, and it did not take long. For the first few millionths of a second, there were no protons at all. Only a searing soup of quarks, the smaller pieces that protons are built from. Once the universe cooled to about 2 trillion degrees, roughly 30 microseconds in, that soup condensed into protons and antiprotons, and the two sides went hunting for each other. Almost all of them found what they were hunting and vanished into radiation. Everything that exists now is the handful that never met its partner. And here is the subtlety that matters. That cancellation did not create the imbalance, it only revealed it. Whatever tilted the scales had happened far earlier, at far higher energies, and the annihilation merely cleared everything else away until only the tilt was left standing. So the mere fact that anything survived tells us the balance was not perfect. The only way to learn how imperfect is to go back to that light and count. So how lopsided was that balance? Barely at all, and that is the unsettling part. Here is how we can even know. What remains of that great cancellation is a faint glow that still fills the entire sky. The oldest light that can still reach us, grown bitterly cold. Arno Penzias and Robert Wilson, two radio engineers at Bell Labs in New Jersey, stumbled onto it in 1965. They were chasing a persistent hiss in their antenna, a noise they first blamed on pigeons roosting inside it. What they had actually found was the afterglow of the beginning, and it won them a Nobel Prize 13 years later. And that glow can be counted. Even today, every cubic centimeter of space holds about 400 particles of that ancient light. Count those against the ordinary matter that survived, and the tally comes out at roughly 1.5 billion photons for every single proton in existence. That ratio is the fossil of the imbalance. Work it backward, and it means that in the first moments, for every billion particles of antimatter, there were about 1,000,000,001 particles of matter. One extra per billion. 1 billion pairs cancelled for every particle that walked away, and that lone survivor is everything. Every star you have ever seen, every person you have ever loved, the ground beneath all of it, is the one part in 1 billion that was never cancelled out. If the scale had sat level, the sky would be that glow and nothing else. Its warmth, almost entirely spent, fallen to just 2.7 degrees above absolute zero, with no one anywhere to feel the cold. And no one yet knows who or what leaned on the balance to leave that one part behind. The reason is missing, and its absence is one of the deepest unsolved problems in physics. It begins with a quiet man who found antimatter on paper, inside an equation, years before anyone caught a single piece of it. Paul Dirac was, by most accounts, the strangest mind in 20th century physics. English, painfully literal, so sparing with speech that his Cambridge colleagues half-seriously defined a unit of conversation, the Dirac, as 1 word per hour. In 1928, he was chasing a problem that had defeated everyone else. Quantum mechanics described the very small. Relativity described the very fast. The electron was both at once, and no equation could handle it that way. Dirac found one. He was 25 years old. His equation worked beautifully, and then it did something nobody had asked for. It produced a second set of solutions, describing a particle identical to the electron in mass, but carrying the opposite charge. Nothing like that had ever been seen. Dirac could have dismissed it as a mathematical artifact, which is what most physicists of the day would have done. Instead, he trusted the mathematics over his own intuition and said, in effect, that the thing must exist because the equation insists on it. 4 years later, a young American named Carl Anderson was photographing cosmic rays at Caltech when one track curved the wrong way through his detector. Same mass as an electron, opposite charge. Dirac's ghost particle, caught on film in 1932. Anderson named it the positron. Dirac collected the Nobel Prize the following year at 31, and Anderson collected his 3 years after that. The implication is stranger than the discovery. A man wrote symbols on paper, noticed they demanded a mirror world nobody had ever observed, and the universe turned out to agree. The rules did not merely permit an opposite for the electron, they insisted on one. And once that sinks in, the discomfort arrives fast, because if every particle has a twin waiting to cancel it, then the mirror is not some exotic corner of physics reserved for laboratories. It is everywhere, including inside you. Your body holds roughly 5 ounces of potassium, most of it locked in your muscles, doing the quiet work of firing your nerves and beating your heart. Almost all of it is stable, but about 1 atom in every 8,000 is a restless isotope called potassium-40, forged in stars that burned out long before the sun existed. It has a half-life of more than 1 billion years, and it does not care that it currently lives in you. Around 4,400 times every second, one of those atoms comes apart. Nearly every one of those breakups spits out an ordinary electron. Roughly once in 100,000, it does something else. It spits out an anti-electron, a positron, a speck of genuine antimatter manufactured in your tissue by you without your permission. The thing lasts almost no time at all. Within a few billionths of a second, the positron blunders into one of your own electrons. And the two do exactly what matter and antimatter always do. They cancel. Their mass turns into two small flashes of light, each carrying 511,000 electron volts, tearing away in opposite directions and straight out of your body. The arithmetic comes to about 160 of these every hour, roughly 4,000 a day. Every day you have been alive. So you are not a spectator to the war that emptied the early universe. You are still hosting it. A few thousand tiny cancellations a day, going off in your muscles like flashbulbs nobody can see. The only reason it does not matter is that inside you, matter outnumbers antimatter overwhelmingly, by the very same lopsided margin that let the universe survive its first minute. Matter wins in your body for exactly the same unexplained reason it won everywhere else. And still, nobody can tell you what that reason is. Somebody did work out what the reason would have to look like. In 1967, a Soviet physicist named Andrei Sakharov published a paper barely 3 pages long, asking what conditions the early universe would have to meet in order to end up holding any matter at all. Sakharov is an odd man to find at the root of this question. He had spent the previous 15 years designing the Soviet hydrogen bomb, and he was extremely good at it. He would spend the next 15 being punished for turning against the state that built it. And he collected the Nobel Peace Prize in 1975 while under surveillance and forbidden to travel to accept it. His paper set out 3 requirements. Think of it as a recipe. First, the universe has to be able to break the balance at all, meaning some process must be capable of producing a particle of matter where the books say there should be none. Second, the laws of nature must not treat matter and antimatter as perfect equals, because if they did, any tipping one way would be undone by identical tipping the other. Third, and this is the requirement everyone forgets, the universe has to fall out of step with itself at the crucial moment. If everything stays in perfect balance, whatever reaction creates the surplus will run just as happily backward and erase it again. All 3 or nothing. Miss a single one and the books close, the twins find each other, and the sky goes dark and even. Sakharov wrote this down as a sketch, almost as a provocation, with no way of knowing whether nature actually satisfied any of the 3. We have spent nearly 60 years checking. The answer is worse than anyone expected. The second condition fell first, and it fell in our favor. In 1964 at Brookhaven, James Cronin and Val Fitch were studying a peculiar particle called the neutral kaon when they caught it breaking the mirror. Matter and antimatter, it turned out, are not exact equals after all. The difference is minuscule, showing up in roughly 1 decay out of 500, but it is real, and it earned them the Nobel Prize in 1980. Sakharov's second requirement exists in nature. We have watched it happen. Then comes the arithmetic, and the arithmetic is where everything falls apart. Take the asymmetry the standard model can actually generate out of that tiny mirror breaking, compare it against the surplus we measure in the sky, and our best theory of matter comes up short by about 10 orders of magnitude. Not 10%, not 10 times, 10 billion times too little. The standard model can account for roughly 1 part in 10 billion of the thing that let you exist. The third condition is worse because there our theory does not merely underperform, it fails outright. Sakharov needed the universe to fall out of balance at the crucial moment, and for decades physicists assumed it obliged, with a violent transition as the Higgs field switched on. Then the Higgs was found in 2012, and it weighed 125 giga-electron volts. At that mass, the transition is not violent at all. It is a smooth crossover, closer to butter softening than to ice cracking. Nothing snaps. Nothing falls out of step. There is no moment for a surplus to freeze into. So the scorecard reads badly. Of Sakharov's 3 requirements, the most successful theory in the history of science satisfies one, misses another by 10 orders of magnitude, and fails the third completely. Whatever wrote you into existence, it was not the physics we currently know, which leaves one uncomfortable possibility still standing. Perhaps the antimatter never vanished at all. Perhaps it is simply somewhere else. Perhaps it is simply somewhere else. Somewhere out past the galaxies we know, a region where the other side won, where anti-stars burn in anti-galaxies and everything is built from the mirror. It is a reasonable thought, and it runs into a wall immediately because you could never tell by looking. Light is its own opposite. A photon emitted by an anti-star is identical to a photon from an ordinary one in every measurable way. An entire anti-galaxy would look exactly like a galaxy through any telescope ever built or ever imagined. On this question, the sky simply refuses to answer. So physicists stopped looking at the objects and started looking at the seams. Any place where a region of matter touched a region of antimatter would have to blaze. Not glow, blaze, with annihilation running along the boundary and pouring out gamma rays at a very specific energy. In 1998, Andrew Cohen, Alvaro de Rajula, and Sheldon Glashow, the last of them a Nobel laureate, calculated how bright those seams would be and compared the answer to the actual gamma ray sky. There were none. No seams anywhere. Their conclusion, under standard assumptions, was that any antimatter region would have to be larger than roughly 3 billion light-years across, which is another way of saying that our side is essentially the whole visible universe. The hunt narrowed to smaller hiding places. Bolted to the outside of the space station, a detector called AMS has been sifting cosmic rays since 2011, and out of some 700 million helium nuclei, it has flagged 8 that might be anti-helium. Anti-helium matters because ordinary collisions can barely manufacture it. So a confirmed one would be a genuine smoking gun. Those 8 have been argued over since 2018 and have never been published. Not confirmed, not refuted. Meanwhile, the Fermi telescope combed almost 6,000 gamma-ray sources, hunting anti-stars, produced 14 candidates that are almost certainly ordinary pulsars, and set a limit instead. At most, 1 anti-star for every 400,000 ordinary ones. So the honest verdict is that we have found nothing confirmed, and that verdict carries a sting. The antimatter did not retreat somewhere and hide from us. It annihilated all of it in the first second, and the faint glow filling the sky is the ash, which means the surplus survived. But surviving was only the first thing your existence required, because that leftover matter could still have spread into a perfectly smooth, featureless haze. A smooth haze builds nothing. No stars, no planets, no one. To become anything at all, what survived had to stay uneven. And there is a law, older and more merciless than any of this, whose entire purpose is to make things even. You already know this law, even without its name. Heat flows from hot to cold, and never the other way. Coffee cools to room temperature and never spontaneously reheats. Smoke leaves a fire and never gathers itself back into the log. Shatter something, and no amount of patience will unshatter it. Each of those is one rule wearing different clothes. And in 1865, a German physicist named Rudolf Clausius finally gave the quantity behind it a name. He called it entropy, and the rule became the second law of thermodynamics. Something sets this law apart from everything else in this story. It has no known exceptions. Not one, anywhere, ever. Physicists will cheerfully tell you that relativity might need amending, that the standard model is incomplete, that below the Planck scale gravity and quantum theory work together fine, and nobody has any idea what happens above it. Nobody says that about the second law. Arthur Eddington put it bluntly, and he was not exaggerating for effect. If your theory contradicts the second law, he wrote, There is nothing for it but to collapse in deepest humiliation. What the law says is simple enough. In any closed system, disorder does not decrease. Sometimes it holds steady. Overwhelmingly it grows, and it grows in one direction only, which makes the second law the only fundamental law in physics that knows the difference between the past and the future. Every other equation runs equally well in reverse. This one does not. That should unsettle you more than it does. Because if disorder only ever climbs, then the universe is not drifting. It is going somewhere specific. Everything runs down. Everything spreads out. Everything creeps toward the same temperature and then stops. Physics has a name for that destination, and it is the least dramatic and most final phrase in the whole of science. The phrase is heat death. It is not poetry, and it is not a fringe scenario. It is the mainstream forecast for the universe, worked out in as much detail as anyone can manage. In 1997, two astrophysicists, Fred Adams and Gregory Laughlin, published a paper in Reviews of Modern Physics that read "The Future the Way a Geologist Reads Rock," splitting it into eras with dates attached. We live in what they called the Stelliferous Era, the Age of Stars. It opened about 1 million years after the beginning, and it closes roughly 100 trillion years from now, when the smallest and stingiest red dwarfs finally burn through the last of their hydrogen and go dark. 100 trillion years is 700 times the age of the universe so far. Held against what follows, it is the opening credits. After the stars, the leftovers. White dwarfs cooling, neutron stars cooling, everything cooling, for a stretch of time long enough that the numbers stop meaning anything to a human brain. Then even those are gone, swallowed or scattered, and for a while, the only significant objects left are black holes, which are themselves slowly leaking away. The largest of them takes something like 10 to the 100th power years to finish evaporating. Write that out and it is a 1 with 100 zeros after it. Then nothing. A thin, cold, uniform haze, spreading forever at almost exactly the same temperature everywhere. Here's the part worth sitting with. Heat death is not a catastrophe. Nothing explodes, nothing comes to get you. It is the absence of events, permanently, because events need difference. Hot next to cold, dense next to empty, ordered next to disordered. Every difference is a fuel, and the second law spends them. When the last difference is gone, no chemistry can occur, no thought can occur, nothing can occur. Forever. And that is not the accident. That is the destination the laws were always steering toward. You are what happened on the way. To see why order is such a scandal, you have to meet the man who put a number on it. Ludwig Boltzmann was an Austrian physicist working in the 1870s, and he is the reason we can speak about heat and disorder in terms of atoms at all. He founded the field we now call statistical mechanics. His strange question was not what heat is, but how many ways a thing can be arranged. Think of the air in the room around you. There are countless ways for those molecules to spread out and fill the space evenly, and only a vanishingly small number of ways for them all to crowd into one corner and leave the rest empty. Spread out looks ordinary because nearly every arrangement looks like that. Bunched in a corner looks impossible because almost none do. That gap, between the many messy arrangements and the few tidy ones, is what Boltzmann turned into hard mathematics. He compressed the whole idea into a single line, now carved on his gravestone. S equals K log W. Take it one piece at a time. The W is the number of different ways the pieces of something can be arranged, while it still looks the same to you. The S is the entropy, which you can treat as how much disorder that number allows. The K is Boltzmann's own constant, about 1 1/3 times 10 to the minus 23. A value so basic that today it helps define what a single degree of temperature even means. The log is only there to keep W from ballooning past all sense. So the line says one plain thing. The more ways something can be scrambled and still look the same, the higher its entropy, and the more the universe favors it. Order is the opposite. Order is low entropy, the state with almost no arrangements on its side. And here is what that costs you. Nature, left to itself, always slides toward the many and away from the few. A living body, a spinning galaxy, a memory holding its shape. Each is an arrangement so specific that the odds against it dwarf the number of atoms in the observable universe. Boltzmann proved it in numbers his own colleagues spent decades refusing to accept, because accepting them meant accepting that everything solid is temporary and staggeringly unlikely. The math he left behind is quiet and merciless. By its logic, you're not a typical outcome. You are the air that crowded, against every odd, into one warm corner of an empty room and held its shape there. And that corner is always, quietly, coming apart. Coming apart in one direction, always. And that one direction is the thing you have never once questioned. Yesterday happened. Tomorrow has not. You remember your childhood and not your final hour. Every waking moment of your life has run the same way, without a single exception. So it should land badly to learn that physics cannot find that direction anywhere in its own laws. The man who noticed was a friend. Johann Josef Loschmidt was older than Boltzmann, an Austrian who in 1865 became the first person to work out roughly how large a molecule is, back when respectable physicists still doubted molecules existed at all. When a man like that raised an objection, Boltzmann could not wave it away. Go down to the individual particles, Loschmidt said, and every law governing them runs backward exactly as well as forward. A film of two atoms colliding, played in reverse, breaks no rule of physics. Nothing in the equations marks which way is forward, which means that if your entire life were filmed at the level of atoms and the reel were run backward, not one frame would violate a law of nature. The universe has no rule against it. It simply never happens. Loschmidt pushed harder. Take anything sliding into disorder and imagine reversing the motion of every particle inside it, at the same instant. The laws allows that. Entropy would fall, smoke would gather back into the log. Your coffee would warm on its own. Nothing forbids a second of it. Boltzmann's answer took years. Physics still gives it today, and it is worse than the question. The arrow of time is not in the laws. The laws do not care. Time runs one way for us only because the universe began in one very particular state, and everything since has been sliding away from it. So, the direction you have lived in every day of your life is not a rule of nature. It is an inheritance. Every memory you hold, every scar, the whole difference between what has happened to you and what has not, is balanced on a single unexplained fact about how things started. That unexplained fact has a number attached, and it is the largest number anywhere in science. It is also, in a way nobody enjoys, about us. Start with what we can measure. The oldest light in the sky, the same glow that counted the antimatter for us, is smooth. Absurdly smooth, reading the same temperature in every direction to about 1 part in 100,000. That is the fingerprint of a universe that began in an extraordinarily orderly state. And orderly, as Boltzmann taught us, means staggeringly few arrangements out of everything available. Roger Penrose tried to say how few. He used black hole physics to fix the ceiling. Gather every particle in the observable universe into one black hole, and the entropy of that object comes to about 10 to the 123. The count of possible arrangements is that quantity as an exponent. So the odds of a beginning as tidy as ours land at roughly 1 in 10, raised to the power of 10, raised again to the power of 123. Nothing in your experience prepares you for that number. It carries more zeros than the universe has atoms, by an unfathomable margin. There is no room to write it down. There is not enough universe to write it in. And every ordered thing you have ever cared about, the star that forged your carbon, the cell that became you, the memory you were holding a moment ago, is drawing on that beginning. We are not simply living in the universe, we are spending it. Now the part almost everyone gets wrong, and it matters more than the number. You have probably heard this figure offered as proof that somebody aimed. It is not. Penrose was an atheist, and his image of a creator taking aim with a pin was a device to dramatize a problem, not a conclusion he held. What the number measures is narrower and, if anything, worse. It measures how absurdly special the beginning had to be for time to have a direction at all. And Penrose would be the first to say it is not even a probability in the strict sense, because nobody knows how to count possible universes, and no agreed theory of gravitational entropy holds it up, which leaves us somewhere uncomfortable. Physics cannot tell us why the universe began so orderly. It can only tell us that it did, that we have been living off the difference ever since, and that the alternative outnumbered us by a margin nobody can write down. By now, an objection should be forming, and it is the right one. If disorder only ever grows, how did any of this get built? A star is not disorder. A galaxy is not disorder. You, with your organized bones and your working memory, are the least disorderly thing for 100 million miles. The second law is supposed to be the most reliable rule we have. So how has the universe spent 14 billion years getting more organized rather than less? The answer is the strangest thing gravity does, and hardly anyone mentions it. Start with how gravity handles heat, because it behaves like nothing else. Let a cloud of gas in a room lose energy and it cools, the way everything you have ever touched cools. Let a cloud of gas the size of a star lose energy, and its core does the opposite. It contracts, and the squeeze drives the temperature up. Physicists call that negative heat capacity, and it is the reason stars exist at all. A ball of gas heavy enough to fall inward heats itself by falling until the middle is hot enough to fuse. The sun is not a fire somebody lit. It is a collapse that got hot enough to fight back. That same inversion runs straight through the entropy books. For ordinary matter, spreading out evenly is what high entropy looks like. Under gravity, it is the reverse. The smooth, evenly spread state is the low entropy one, and clumping is where the entropy goes, not because lumps are disorder in themselves, but because collapse dumps enormous quantities of heat and radiation and stray matter into everything nearby, and the ledger of the whole system climbs the entire time. Push it to the end, and you get a black hole, the highest entropy object the universe knows how to build. The gap there is not close. The sun, all of it, carries an entropy of roughly 10 to the 58th. Collapse that identical mass into a black hole, and the figure leaps to about 10 to the 77th. 19 orders of magnitude from the very same material, differently arranged. So the smooth beginning was not merely tidy, it was a loaded spring. A perfectly even universe under gravity is a universe wound tight, and every star that has ever lit is that spring unwinding. Structure is not a rebellion against the second law. Structure is the second law, running through the one force that rewards collapse. Physicists will tell you plainly that they still have no agreed formula for the entropy of gravity itself, that this remains one of the open holes in the subject. What none of them doubt is the direction, which means the law did not spare you. It built you on the way down, and it has never once stopped charging for the privilege. The charge lands every second, and the sun is what pays it. Erwin Schrödinger, one of the founders of quantum mechanics, worked this out in February 1943 in a series of public lectures in Dublin that became a small book the following year. He was asking what life physically is, and the answer sounds strange until suddenly it does not. A living thing does not feed on energy. Energy is conserved, so you cannot consume it, and you hand back every joule you take. What an organism feeds upon, he wrote, is negative entropy. It stays alive by pulling in order and pushing out mess, and the gap between those two piles is the only thing keeping you shaped like a person. He was uneasy about that phrase almost at once. In a note added to the chapter, he admitted his fellow physicists would have preferred the technical term free energy, but that he feared readers would hear the word energy and miss the entire point. He was right to worry. The point was never energy. The point is order. Behind that trade sit some stark numbers. Sunlight arrives as a trickle of high-energy photons thrown off a surface at nearly 6,000 degrees. Earth radiates back as infrared, from an effective temperature of about -18. The energy going in and the energy going out balance almost exactly, but colder light carries less energy per photon, so the count cannot balance. For every single photon of sunlight this planet swallows, it coughs back more than 20 infrared ones. Earth is not gaining energy from the sun. Earth is laundering entropy, taking in a little order and exporting a great deal of mess, and every living thing here sits downstream of that one transaction. You are part of it. At rest, you run at about 80 watts. Go about an ordinary day and you are closer to 100, roughly a bright old light bulb, and nearly all of it leaves you as heat. That warmth coming off your skin is not a byproduct. It is the payment. Every thought you have had, every memory you have held in order, was funded by pushing more disorder into the room than you assembled inside yourself. Schrödinger's little book did one more thing. It landed in front of a generation of physicists and sent them hunting for the physical object that carries heredity. 10 years later, Francis Crick wrote to him to say exactly that he and Watson had both been steered into biology by those lectures. The man asking why order is possible at all had, without intending to, pointed the way to the molecule that holds yours together. So you are not exempt from the second law. You are one of its more elaborate customers, and every customer eventually runs out of credit. Credit is the right word, because none of this is owned. All of it is borrowed. Consider what the sun is actually doing to settle your account. Every second, it converts about 4.25 million tons of its own mass directly into energy. Not burns, converts. That is Einstein's line from earlier running at industrial scale. Mass turning into light at 4 million tons a second, without a pause, for 4.5 billion years. Add the particles it flings off as solar wind, and the total loss climbs to roughly 5.5 million tons every second of every day. It can afford that for now. The sun has fused through about half the hydrogen in its core, which is the only part of it that ever gets hot enough to burn. In another 5 billion years, the core will finish. The star will swell, shed its outer layers, and settle into a white dwarf to cool for the rest of time. You will not get 5 billion years, and here the honest number is far worse than the famous one. The sun is not steady. It brightens as it ages by something like 10% every billion years, and that is more than enough. Somewhere between 1 and 2 billion years from now, the rising heat strips the carbon dioxide out of the air or drives the oceans off into space, depending which mechanism arrives first, and complex life on the surface is finished. Not in 5 billion years. In 1 or 2. The window for anything like us is already most of the way shut, and nothing about that is a prediction of catastrophe. It is just the bill, arriving on schedule. So your existence is not a state. It is a transaction, still running, with a balance that moves in one direction only. The order you are made of came out of that absurdly special beginning, and it has been draining ever since, through the sun, through the stars, through you. That absurdly special beginning is a problem physics cannot solve, and it has dealt with the problem in the way you would least expect. It wrote the problem into the rules as an assumption and carried on. Richard Feynman said it plainly in a lecture in 1964, and it remains one of the quietly most alarming sentences in the subject. It is necessary, he said, to add to the physical laws the hypothesis that in the past, the universe was more ordered than it is today. Add to the laws, not derive from them. The equations cannot produce the arrow of time on their own, so we hand them the past as a gift, and let them run forward from there. Decades later, the philosopher David Albert gave that gift a name, the past hypothesis, and it has been called that ever since. Naming it did not domesticate it. Every prediction you have ever heard a physicist make about the future, that the ice will melt, that the star will cool, that your coffee will not reheat itself, is standing on a claim about the first moments that nobody can derive, test directly, or explain. Feynman pushed it further, in a way that is going to matter to us before the end. He asked whether our tidy corner might simply be a lucky fluctuation inside an otherwise disordered universe, and then showed why not. If the order around you were a fluke, everywhere you had not yet looked should be a mess. Dig up one dinosaur bone, and there should be no second bone waiting nearby. But there is always a second bone. The order keeps holding, everywhere anyone checks, which means it was not a fluke. It was inherited. He was quietly dismantling an idea that will come back for us later, wearing a far stranger face. And not everyone accepts the fix. In 2006, the philosopher of physics John Earman published a paper on the past hypothesis with a title that hands you the verdict up front. Not even false. His argument is that once gravity is in the picture, the entropy of the universe may not be a well-defined quantity at all. In which case, the assumption everything is resting on is not merely unproven. It is not yet a coherent thing to say. So this is where the ground actually sits under you. The direction of time works. The predictions come out right every single time for everyone forever. And underneath them lies an assumption about the beginning that physics cannot justify, cannot test, and cannot even agree is meaningful. It holds anyway. That is the arrangement, and nobody has found a better one. Though the arrangement only pays out at all if the numbers underneath it are exactly the values they are. And nothing in physics says they had to be. Nothing in physics says they had to be. And you are carrying the proof of that around in your body right now without noticing. Whatever you weigh, almost none of it is stuff. You are mostly protons and neutrons. Every proton holds 3 quarks, and if you add up the mass of those 3 quarks, they come to roughly 1% of the proton. 1%. The other 99 is not matter at all. It is not binding energy either, because binding makes things lighter, which is why a helium nucleus weighs less than its parts, and why that missing weight powers the sun. This runs the other way. The proton weighs 100 times more than the quarks inside it. What you are weighing is the churn. Near massless quarks moving at almost the speed of light. The gluon fields trapping them, and a quantum effect with no classical counterpart at all. Roughly a third motion, a third field, the rest something stranger. Energy boxed into a proton-sized volume simply as mass. So when you feel your own body pressing into a chair, you're not feeling stuff. You're feeling a force. 99% of you is tension. And here is where the ground softens. The strength of that force is one of the numbers. Not derived, not predicted, not explained. Somebody measured it, wrote it down, and hand-fed it into the equations along with 18 others. 19 in total, 26 once you count the neutrinos, and the entire standard model, the most accurate theory our species has ever built, runs on them without ever being able to say where a single one came from. Ask that theory for the magnetic strength of the electron, and it matches the measurement to about 1 part in a trillion, near enough to predict the distance to the moon and miss by a hair. Nothing else we have made comes close. Ask it why the strong force sits at the value that sets 99% of your body weight, and it has nothing. Not a wrong answer. No answer at all. Which leaves the obvious question standing in the open. How far would that dial have to move before nobody is left to ask? For about 40 years, physics believed it had a clean answer, and that answer became one of the most instructive mistakes the field has ever made. The answer went like this, and you have almost certainly heard some version of it. Take the strong nuclear force, the one holding atomic nuclei together against the electric repulsion, trying to tear them apart. Turn it up by a couple of percent, the story goes, and 2 protons will stick to each other. That object, a diproton, does not exist in our universe, and the story says its existence would be a catastrophe. Protons would fuse the moment they met. Hydrogen would burn away in the opening minutes. No fuel left for stars, no water, no chemistry, no you. A knife edge 2% wide, and everything you are is balanced on it. It is a beautiful argument. Freeman Dyson raised it in 1971, Bernard Carr and Martin Rees carried it in 1979, Barrow and Tipler built it into their book in 1986. Rees put it in front of a mass audience in 1999. For 4 decades it appeared in lectures, in textbooks, in documentaries, as one of the cleanest pieces of evidence that the universe is balanced on a needle for our benefit. In 2008, a physicist named Robert Bradford did the one thing nobody had bothered to do. He calculated it. The whole argument, it turned out, rested on a false analogy. 2 protons are identical particles, and that changes everything. Being identical shuts down the usual routes by which a pair fuses, leaving only a feeble channel roughly 100,000 times weaker. Diprotons do not burn the hydrogen away because they barely burn at all before the early universe cools out from under them. Bradford turned the strong force up by 40% and still got a cosmos that comes out about 3/4 hydrogen, the same as ours. Then it got worse for the story. In 2015, Luke Barnes, who was the leading academic defender of fine-tuning, published on the question and gave his finding a title with no room in it. There is no diproton disaster. Stars with bound diprotons still work. They settle at different densities and temperatures and go on burning regardless. So the most repeated number in the fine-tuning canon spent 40 years being passed hand to hand by the most eminent people in the field, and it was wrong. Not wrong because the physics was hard. Wrong because of an analogy that nobody checked. Which does not mean nobody ever got it right. One man landed a prediction so clean it still gets taught, and his case is the one worth telling properly, including the part where the telling went wrong. Fred Hoyle was an English astronomer, Yorkshire-born, famously abrasive, and the man who worked out how stars build the periodic table. He is a large part of the reason there is carbon in you at all. In 1953, he was wrestling with a problem that had beaten everyone. Stars fuse hydrogen into helium easily enough, but getting from helium to carbon means sticking 3 helium nuclei together, and the halfway house is a nucleus called beryllium-8 that falls apart in about 1/10 of a quadrillionth of a second. The window is absurdly thin. On paper, carbon should barely exist. Hoyle reasoned backwards from the evidence in front of him. Carbon is abundant. Stars are where it comes from. So the reaction has to be far faster than the numbers permit. And the only thing that could manage that is a resonance, a specific energy level inside the carbon nucleus that lets 3 heliums lock together in the instant available. He did not merely say a resonance ought to exist, he said what energy it should sit at, around 7.68 million electron volts. And then he walked down the hall at Caltech and told the experimentalists to go and find it. They were not keen. Ward Whaling's group ran the measurement anyway. The level was there, at 7.68, inside the error bars. The modern value is 7.654. It stands as one of the cleanest predictions in the history of nuclear physics, made by a theorist with no data, purely on the strength of an argument about what stars must be doing to produce what we see. That is the real story, and it is extraordinary without any help, which is exactly why what happened to it next is worth your attention. Here is the version you have almost certainly heard. Hoyle predicted the carbon level because he knew that carbon-based life exists, and reasoned that the universe must therefore be built to allow carbon. Your own existence, used as laboratory evidence. It is the founding story of the entire fine-tuning idea, retold in 100 books and 1,000 lectures. It did not happen. The historian Helga Krag went back through the record itself. Papers from 1953, private letters, what Hoyle and the people around him were actually writing at the time. Life is not in there. Not once. Hoyle's argument was about the abundance of carbon in stars, an observation that came from spectroscopy, not from biology. He was solving a problem in how stars build elements, and living things had nothing to do with any of it. The anthropic reading was fastened on later, in the 1980s, once that style of reasoning came into fashion, and then read backwards into a 30-year-old result. Hoyle did eventually say something close to the famous line. He said it in 1981, 28 years after the prediction, in a Caltech magazine. A common-sense interpretation of the facts, he wrote, suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology. That sentence gets quoted constantly, usually with a meaningful pause afterwards. What gets left out is that Hoyle rejected any personal god, and what he meant by super intellect ran somewhere naturalistic and cosmic, and frankly odd, closer to his own theories about life drifting in from space. So the flagship exhibit in the case that the universe was arranged for your benefit is a genuine prediction with a false story bolted onto it, plus a quotation lifted out of a context that inverts it. Nobody lied. Everybody simply repeated. And that should land somewhere uncomfortable, because you did not check either. Neither did I. Everything you believe about why you are here came down a chain of people trusting the person in front of them, and the chain is far too long for any of us to walk back. The Dipperton spent 40 years in that chain, wearing a lab coat. Nobody in it was lying. That is what makes it frightening rather than merely embarrassing. Hold on to that, because it is about to happen again, with a much bigger number. It happens again with the largest figure anyone quotes in this argument, and it happens the same way. You will hear that the energy of empty space, the cosmological constant, is tuned to 1 part in 10 to the 120th. A 1 followed by 120 zeros. Move the dial a single notch anywhere in that span, the story goes, and there is no you. It is the most repeated statistic in the whole fine-tuning canon. The number is real. It is also answering a completely different question from the one it gets used for. 10 to the 120 is the gap between what quantum theory says empty space should weigh and what we measure it to weigh. It is a fight between two calculations, a scandal about our own physics, and we are going to get to how bad that scandal is shortly. It was never a statement about how much room you had. The question about you was answered by Steven Weinberg in 1987. Turn the cosmological constant up and space expands faster. Turn it up far enough, and it tears matter apart before gravity can drag it together into galaxies. Weinberg worked out where that line falls, and it is nowhere near 120 orders of magnitude. It sits at a factor of a few hundred. Then it loosened further. In 2018, Luke Barnes and his colleagues put the question through the Eagle simulations, building entire model universes with the constant cranked up. 10 times our value barely scratches star formation. You need roughly 30 times before the damage starts, because the cosmos does most of its star building early, billions of years before the constant gets its hands on anything. And here is the part that should sting anyone selling this. The dependence is gentle. Barnes and his co-authors concluded that the effect on structure is not a sharp enough function of the constant to explain why it sits where it does. So the crown jewel of anthropic reasoning, the one case where the universe supposedly had no choice but to be this way for us, does not deliver. And it fails in the direction that damages the multiverse rather than the one that rescues it. 2 numbers then. One is 120 orders wide and has nothing to do with you. The other is a few hundred wide and cannot explain itself. Nearly everyone quotes the first while meaning the second, because there is an escape, and you have heard this one too. Suppose ours is not the only universe. Suppose the dials get set at random, over and over, across an enormous crowd of separate cosmoses, and nearly every one of them comes out barren. Here is the move that follows, and it is the entire argument. A barren universe has nobody inside it. No stars, no chemistry, nobody standing there to be surprised by anything. So a failed universe never gets examined, because there is no one in it to do the examining. The only cosmos anybody ever looks at from the inside is one that happened to work, which means finding yourself surrounded by friendly numbers is not evidence of anything at all. It is a foregone conclusion. You could not have turned up anywhere else. Nobody could. It is the same reason every person you have ever heard describe surviving a plane crash survived one. 2 pieces of real physics hold this up. The first is eternal inflation. Run most versions of our theory of the early universe forward, and the expansion never quite stops everywhere. It just keeps budding off new bubbles, each sealed away as its own separate cosmos. The second is string theory, the leading attempt to fit gravity and quantum physics into one framework. It only works if space carries more dimensions than the 3 you move through, with the extra ones curled up far too small to notice, and how you curl them decides what the constants come out as. Fold the hidden dimensions one way, and you get one set of numbers. Fold them differently, and you get another universe entirely. The number of possible folds is astronomical. Then, you ask the whole arrangement to predict something, and it cannot. The obstacle is called the measure problem, and it is fatal in a precise way. Eternal inflation does not make many bubbles. It makes infinitely many. To predict anything, you have to ask what fraction of observers see what, and with infinities, the fraction depends entirely on the order you count them in. Count one way and the cosmological constant comes out beautifully. Count another and it does not. Nothing inside the theory tells you which order is right, so you supply that yourself, by hand, and the answer obediently follows whatever you chose. Barnes and his colleagues put it flatly in that same 2018 paper. Whether the multiverse successfully predicts our constant depends crucially on the measure used, which means it predicts nothing until you have already decided what you wanted to say. So this is the comfort on offer. An unimaginable crowd of failed universes, and you standing in the one that worked, for no reason anyone can name. It accounts for the tuning by declining to account for anything, which leaves the puzzle where it started, minus most of its evidence. Except for one number nobody has managed to bring down. You have already met that number, though it went past without a name. That 100,000th of a degree of roughness in the ancient light, the one that told us the beginning was absurdly smooth, has a name. Physicists call it Q, and it is the size of the ripples the universe was born with. Q is what everything grew from. Gravity took those ripples and dragged them into galaxies, into stars, into the atoms that became you. And unlike the diproton, unlike the story pinned onto Hoyle, unlike the 120 orders of magnitude, Q has survived every audit anyone has run at it. Turn Q down below roughly 1 in a million, and the ripples are too feeble to matter. Gravity still gathers gas, but only into clouds too loose and too cool to ever ignite. Either no stars form at all, or the few that manage it cannot hold on to the heavy elements they make, and everything they built drifts away into the dark. Turn Q up above roughly 1 in 10,000 and the opposite arrives. The cosmos turns violent, matter clumps too hard and too early, galaxies come out dense and supermassive, stars crowd each other closely enough to rip planets out of their orbits before anything on them has time to happen. Push it further and the lumps collapse straight into black holes, without ever bothering to be stars. Between those two failures sits a window about 2 orders of magnitude wide. That is the entire space you were allowed. Martin Rees and Max Tegmark mapped it in 1998, and unlike the celebrated claims that dissolved the moment somebody checked them, this one is a real free parameter with a real and narrow range, and it has not moved since. Rees would later argue that the whole habitable cosmos hangs on just 6 numbers. Q is the only one of the 6 whose tuning survived inspection intact. So here is the honest state of things, and it is not what either side usually tells you. The evidence did not vanish, it relocated. 40 years of famous numbers turned out to be softer than advertised, and what is left standing is smaller, fewer, and far harder to argue with. Nobody answered the puzzle, it just got concentrated. And the number that survived the call is the one that made you. That same 100,000th of a degree of roughness that handed you a galaxy is sitting inside the tightest window physics has ever found. Which brings us back to the figure we set down and walked past. There were 2 numbers wearing the same clothes. One was a few hundred wide, and that was the room you actually had. The other ran to 120 orders of magnitude and had nothing to do with you at all. It is time to go back to the second one, because it is not a fine-tuning claim and it is not a curiosity. It is the largest failure in the history of physics, committed by our best theory about the emptiest thing there is. And it does not stand alone. Once anyone starts looking properly, our most successful physics turns out to be riddled with numbers it cannot produce, gaps it cannot bridge, and one prediction so catastrophically wrong that the only reason we know it is wrong is that you are here to be told about it. The dials were the easy part. What comes next is where the instruments stop working. Start with empty space and take the word empty seriously. Imagine a box with everything removed. Every atom, every stray photon, every speck of dust. Chill it to absolute zero so nothing inside is moving. What is left in there? Not nothing. The fields are left. In modern physics, particles are not the basic furniture of reality. Fields are filling all of space, always, and a particle is only a ripple traveling through one. Smooth out every ripple and the field is still there, sitting in its lowest possible state. And that lowest state does not hold zero energy. It cannot. Quantum mechanics forbids anything from being perfectly still. You have likely heard this described as particles constantly popping in and out of existence. Set that aside because it is not what happens. That image is borrowed from the bookkeeping inside a calculation, not from any froth of things appearing and vanishing. Nothing pops. The truer statement is stranger anyway. Emptiness is not an absence. It is a substance with a flaw, and the flaw does not sit at zero, and you are sitting inside it. That box is not a thought experiment you can hold at arm's length. It is the space between the atoms of your own hand. Now the crack, which has been in the foundations of physics for a century. Quantum theory only ever predicts differences. Ask it how much energy something has, and it does not answer. Ask how much energy something gains or loses, and it answers to 12 decimal places. That has never been a problem, because nothing in quantum physics cares about the absolute figure. Everything cares about the change, everything except one thing. Gravity does not respond to differences in energy. Gravity responds to energy itself, all of it, absolutely, including whatever empty space is carrying. So the one number quantum theory politely declines to supply is the exact number gravity demands. Physicists tried to force an answer out of it anyway. What came back is the most notorious figure in science. The calculation is not exotic. Every field has a lowest state. That state carries energy, so add up the contribution from every field at every wavelength, and you have the energy of empty space. Students do a version of it. The answer comes back enormous. Not slightly too large, enormous. Set it beside what we actually measure in the sky, and the two differ by something like 120 orders of magnitude. A 1, followed by 120 zeros. Nothing in your experience is that wrong, so there is no comparison that will land. The number of atoms in your entire body is around 10 to the 27th. Every atom in the whole observable universe, in every star, in every galaxy, comes to about 10 to the 80th. Set that against the gap here, which is 10 to the 120th. 40 orders of magnitude larger than every atom in existence. In 2006, in a Cambridge textbook on general relativity, Michael Hobson, George Efstathiou, and Anthony Lazenby wrote the sentence that stuck to it. This is probably the worst theoretical prediction in the history of physics. It gets quoted constantly, usually attributed to Feynman, which is wrong. The line is theirs, and it sits on page 187. The stakes are not academic. If empty space carried anything close to the energy that calculation hands you, it would have torn itself apart in the opening instant. Matter would never have gathered. No galaxies, no stars, no atoms, nobody. You are here because reality ignores our best calculation by 120 zeros, which sounds like the strongest evidence anyone could want that physics is broken. It is not. What actually happened is worse, and almost nobody tells this part. That 120 is a choice. To add up the energy of all those field states, you have to stop somewhere, or the sum runs to infinity. Where you stop is called the cutoff, and the cutoff decides your answer. Stop at the Planck scale, the smallest length anyone thinks is meaningful, and you get around 10 to the 123rd. Stop instead at the energy of the Higgs field, and you get 10 to the 56th. Stop where the strong force lives, and you get 10 to the 44th. Notice what follows from that. The literature quotes 120, 122, 123, more or less interchangeably, and nobody blinks. That spread is not measurement uncertainty. It is the fingerprint of a number that depends on a convention rather than on nature. It gets worse for the famous version. The naive sum is not Lorentz invariant, which is a technical way of saying it computes the wrong thing entirely. Perform it with a hard cutoff and what you get behaves like radiation, not like empty space. And when the calculation is done properly, with the machinery physicists actually use, the absolute energy of the vacuum is not predicted at all. It is an input, measured from the world, exactly like the mass of the electron. So the worst prediction in the history of physics is not a prediction. Quantum field theory never made it. And here is where it should get under your skin, because the honest problem is worse than the folklore. You cannot make the trouble go away. Forget the Planck scale entirely. Take only the contribution from the Higgs field, whose strength we have measured in a laboratory outside Geneva, and whose physics we have tested to exhaustion. That piece alone comes out around 55 orders of magnitude larger than the vacuum energy we observe. You cannot delete it without deleting the Higgs, and the Higgs is not optional. We found it. It is there, which means something is cancelling that number down to 55 decimal places, and nobody can say what. Not a wrong answer. A conspiracy of cancellation running quietly beneath everything you are made of, holding empty space almost exactly flat for no reason anyone can name. Physics did not fail here. Something is doing this, and every second of your existence depends on whatever it is. Whatever it is, we have measured it, and the way we caught it is worth knowing, because it nearly did not work. The tool is a particular kind of exploding star. When a white dwarf pulls too much material off a companion, it detonates, and for a few weeks, it burns brighter than the galaxy holding it. These are Type 1a supernovae, and because they all go off in roughly the same way, they were supposed to be standard candles. Same true brightness every time. So the dimmer one looks, the farther away it is. Except, they are not standard. Their brightnesses scatter by nearly a factor of 2, which is far too sloppy to measure anything subtle. The discovery only exists because of a correction found in 1993 by Mark Phillips, who noticed that the brighter ones fade more slowly. Measure how fast a supernova dims, and you can work backwards to how bright it truly was. That one empirical trick tightened the scatter enough to see the effect. Without it, there is no story. 2 teams went hunting. The Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees as lead author of the paper that landed first in September 1998. Both found the same thing, and neither wanted it. The distant supernovae were coming in roughly 10 to 15% farther away than they should have been in a universe with no vacuum energy at all. Nobody watched the universe accelerate. What they saw was starlight arriving fainter than it had any business being, and the only model that fit had empty space quietly pushing everything apart. The Nobel came in 2011. So nothing was solved in 1998. What happened is that the thing we cannot explain was confirmed to be real, and then measured. It is out there now, in the widening gaps between galaxies, pushing them apart a little more efficiently every year as matter thins out and stops resisting. Everything anyone can see is being carried away from everything else by a number that nobody can derive from anything. That was the situation for 27 years. Then it got worse. In 2025, a machine in Arizona started handing back results nobody was ready for. The Dark Energy Spectroscopic Instrument sits on a telescope on Kitt Peak, and it does one thing on a scale nothing before it managed. It measures the distances to millions of galaxies, building the largest 3-dimensional map of the universe ever assembled. and that map records how the expansion has changed across billions of years. If the energy of empty space is a constant, as the name cosmological constant promises, then its push has been identical at every moment since the beginning. That is the entire assumption. It is baked into every model, every simulation, every forecast of the far future. DESI's second data release says it may not be. The map prefers, at a significance running between roughly 3 and 4 sigma depending on what you fold in with it, a dark energy that is not constant at all. One that was stronger in the past and is weakening now. That is not yet a discovery. 3 sigma has fooled physics before more than once, and the next release is still a couple of years out. But it is the first time the constant has been seriously challenged since we found it. And the challenge is coming from the best data anyone has ever had. Sit with what that would mean. For a century, the problem was why this number is so absurdly, impossibly small. If Deci holds, the problem becomes why this number is moving. A constant that is not a constant. It is something else, something with a history, something doing something, and we would not have the faintest idea what. And it reaches forward. Everything anyone tells you about the end of the universe, the cold, the emptiness, the dark forever, is built on that number staying exactly where it is. If it is drifting, the ending changes. We do not know into what. The map of reality is not just torn. The tear is spreading while we are standing on it. The vacuum is not the only place the map is torn. There is a second tear, and it runs through the thing that lets you have atoms at all. Meet the Higgs field. It fills space the way the others do, and as fundamental particles move through it, it drags on them, and that drag is what we call their mass. The electron gets its mass this way. So do the quarks. Though, as we saw, their masses barely register against the churn inside a proton. But the electron's mass is not a footnote. It sets the size of an atom. Make the electron heavier, and atoms shrink and chemistry changes beyond recognition. Make it lighter, and they will not hold together at all. That 1% the Higgs is responsible for is the 1% that lets you be built. Now, the trouble. In the standard model, every other particle has a shield. Take the electron again. Set its mass to 0, and a new symmetry appears in the equations, and symmetries protect things. It means the quantum corrections to the electron's mass are proportional to the mass itself, so they can nudge it but never run away with it. The force-carrying particles have their own version of the same protection. Every mass in the theory is guarded by a symmetry that keeps it close to where it started. Except one. The Higgs is the only fundamental particle of its kind in the entire standard model, and nothing shields it. Any heavy thing it couples to, known or unknown, drags its mass upward toward that heavy thing's scale. And the scale where gravity finally turns strong sits around 10 to the 19th in the units physicists use, while the Higgs sits at 125. 17 orders of magnitude apart. For the Higgs to be where we found it, the raw number and all those corrections have to cancel to roughly 32 decimal places. A second cancellation. A second conspiracy. Nobody ordered this one either, and the physics that lets you have chemistry is sitting on top of it. Physicists were so certain something must be protecting it that they built a machine partly to find the protector. The favourite candidate was supersymmetry, and it is an elegant idea. Give every known particle a heavy partner, and the partner's contribution cancels the originals. Cleanly, automatically, no conspiracy required. The Higgs would then be light for a reason rather than by accident. Most of the field expected it. Think about what that machine was for. 27 kilometers of tunnel bored under 2 countries, something like 10 billion euros, 30 years from the first sketch to the first collision, and a substantial part of the reason for building it was to find out why you were permitted to be made of atoms. It ran. In 2012, it found the Higgs, sitting exactly where the theory promised, and then it found nothing else at all. Not at 1 tera electron volt, not at 2. The heavy partners are now excluded past 2.4, and the versions of supersymmetry that actually solve the problem are precisely the versions that have been ruled out. What survives is tuned to the percent level, which is another way of saying it no longer solves anything. In 2017, Gian Giudice, one of the idea's own champions, published a paper he titled The Dawn of the Post-Naturalness Era. So the question that machine was built to settle is still open. The finest instrument our species has ever constructed went looking for the reason you are allowed to exist, found the one thing it was told to find, and then found silence. Nobody has a plan for what to do next. So what do our best theories actually say about you? Nothing. And that is not a figure of speech. The standard model does not predict the mass of the electron. It does not predict the strength of the strong force, or the energy of the vacuum, or how hard the Higgs pulls. Those are not outputs. They are inputs, measured from the world and typed in. A theory that takes a number from you cannot turn around and tell you anything about that number. Physics does not predict a dead universe, and anyone who says it does is smuggling in an expectation and calling it a prediction. But we do have an expectation. Exactly one. It is called naturalness, and it is the only tool anybody has for guessing what a number ought to look like before you measure it. The rule is simple. A pure number, with no units attached, should come out somewhere near 1, unless a symmetry forces it elsewhere. That rule has earned its keep for a century. It is how the positron and the charm quark were anticipated before anyone found them. Point that rule at our universe and it fails catastrophically. The energy of empty space needs a cancellation to 55 decimal places. The mass of the Higgs needs 1 to 32. Neither has a symmetry behind it. Both should, by every instinct the field has developed, be nowhere near where they are. And if either sat where the rule says it should, there would be no galaxies, no atoms, no chemistry, and nobody to have this problem. And physics has a word for a number like that. A quantity sitting where no symmetry put it, with nothing accounting for the position, is called unnatural. That is not a flourish. It is the term of art, the one that goes in the titles of papers. Every value that had to fall exactly where it fell for you to be assembled answers to it, which means the numbers you are built out of are, in the plain language of the field, unnatural, and you are what they add up to. That is the honest state of it, and it is stranger than physics being broken. Physics is not broken, it works. It predicts the electron's magnetism to 12 decimal places and lands every time. The trouble is that the only instrument we have for deciding whether a universe makes sense reads, when pointed at ours, that this one does not. Our theories accommodate you. They have never once explained you. And there is one place left for that failure to go. Every gap so far has been about the world out there. The last one is about the thing doing the looking. Because there is a version of this that is worse, and it has been waiting since the beginning of the story. Feynman saw it in 1964, in the middle of the same lecture where he admitted the past has to be handed to physics as a gift. He asked whether our orderly little corner might simply be a fluke, a chance ripple of order in a universe that is otherwise scrambled. He decided it was not, and his reason was elegant. If our order were a fluke, then everywhere we had not yet looked should be a mess. The next fossil should not be there. The next galaxy should not have arms, but the order keeps holding everywhere anyone checks. That answer worked in 1964, when the universe was assumed to be finite in its history and heading somewhere definite. It does not work now. Not with a vacuum energy that never switches off. Not with an expansion that may run forever, into a cold that lasts longer than any number you can write. Because if you give the universe enough time, and there is no obvious ceiling on how much time it has, then Feynman's argument develops a crack, and something crawls out of it. The question stops being why you exist. It becomes whether you did. The idea is older than you would guess, and it belongs to a man we have already met. In 1895, Ludwig Boltzmann sent a letter to nature with a proposal so strange, that it reads today like something out of a much later century. Suppose the universe as a whole is not young. Suppose it is eternal, and almost all of it sits in perfect equilibrium, evenly spread, nothing happening, forever. Given endless time, chance alone will occasionally shove some corner of it into a low entropy state, the way endlessly shuffled air will one day, once, crowd into a corner. We would be living inside one of those accidents, not a creation, a statistical hiccup in an eternal grey. Boltzmann, characteristically, gave the credit to somebody else. The idea, he wrote, came from his old assistant, a Dr. Schutz. For 36 years, it sat there looking clever. Then Arthur Eddington took it apart in a single sentence, and the sentence is the reason this story gets frightening. In 1931, addressing the British Mathematical Association, Eddington pointed out what a fluctuation would actually have to produce, and his answer was, as little as possible. A universe containing mathematical physicists, he said, will at any assigned date be in the state of maximum disorganization, which is not inconsistent with the existence of such creatures. That deserves unpacking, because it is the hinge of everything that follows. Fluctuations get exponentially less likely the more order they have to manufacture. A whole galaxy is astronomically more expensive than a solar system. A solar system is astronomically more expensive than a planet. And a planet, with its 4 billion years of evolution, and its fossils, and its libraries, is astronomically more expensive than the one thing actually required, which is a mind, alone, for a moment, with the memories already inside it. If you are an accident, you are the cheapest accident that could still be having this thought. That thing has a name, and it is not Boltzmann's. The term was coined in 2004 by the physicist Andreas Albrecht, first on a seminar slide and then in a paper with Lorenzo Sorbo. He called it a Boltzmann brain, and the name stuck to something Boltzmann never proposed and would probably have hated. It came back because of the number from earlier. In 2002, Lisa Dyson, Matthew Kleben, and Leonard Susskind published a paper with a title that does not hide its feelings: Disturbing Implications of a Cosmological Constant. Their point was straightforward. If the energy of empty space never switches off, then the far future is not a slow fade to nothing in particular. It is an eternity of faintly warm, empty space that goes on having a temperature forever. And a thing with a temperature is a thing that fluctuates. Run that forward, not for billions of years. For a length of time, you would write as a 1 followed by more zeros than the observable universe has atoms. Across that span, the number of minds that flicker into existence by pure chance, complete with a lifetime of memories that never happened, exceeds the number of minds that got here the ordinary way. Not slightly, exponentially, by a margin that makes the ratio meaningless. Now, here is the thing, almost every telling of this gets wrong, and getting it wrong turns a serious problem into a silly one. No physicist thinks you are a Boltzmann brain. None of them lie awake wondering whether they are one. That is not what this is for. It is a stress test. When a cosmologist runs a model forward and it starts predicting that most observers are freak fluctuations with fabricated pasts, that is not a discovery about observers. It is the model failing. The argument is used in actual working papers as a way of ruling candidate theories out. A theory that predicts you are probably a hallucination has told you something about itself, not about you. The trouble is that our best model of the universe is one of the theories it keeps threatening to rule out. So, why are you probably real? The cleanest answer came from Sean Carroll in 2017, in a paper titled, With No Ceremony, Why Boltzmann Brains Are Bad. His argument is not that we have evidence we are not brains. That would not work, because a brain with your exact memories has your exact evidence. His argument is sharper and stranger. A theory predicting that most observers are Boltzmann brains is what he calls cognitively unstable. It cannot be simultaneously true and reasonably believed. If it is right, then your reasoning is untrustworthy, including the reasoning that led you to it. It soars through the branch it is sitting on. That is elegant. It is also, as of now, an argument under fire. Don Page argued in 2024 that the fancy machinery is unnecessary, because ordinary probability handles it. The range of things a random brain could experience is unimaginably wider than the narrow, coherent, boring range a human experiences. So a coherent human moment is far more expected from a real human than from a fluctuation. Others go further. Adam Elgar published a paper last year arguing that the whole instability is an illusion, and that the argument fails on its own terms. And there is a stranger escape, from Carroll himself with Kimberly Body and Jason Pollock. Their claim is that a true vacuum may not fluctuate at all. A stationary quantum state is, by definition, not doing anything. The vacuum having the potential to contain a brain is not the same as a brain occurring, any more than a die having a 6 on it is the same as rolling 1. If they are right, the empty universe never manufactures anybody, and the problem evaporates. Their escape depends on assumptions about quantum gravity that many in the field reject. So the honest position is this: you are almost certainly not a fluctuation. But the reason is not obvious, it is not settled, and it is not comforting. It is that the alternative destroys its own evidence and takes the rest of physics down with it. We are not standing on solid ground here. We are standing on the fact that the other option is unlivable. Unlivable is a strong word, so look at what the livable option actually leads to. The eras we walked through earlier all still arrive, exactly on the schedule Adams and Laughlin laid out. Stars gone by 100 trillion years, the cinders cooling after them, and then the long stretch where black holes are the only objects left of any consequence, quietly leaking themselves away until the last of them is finished. Here is what that schedule does not tell you, and it should sit badly. In 2010, Chas Egan and Charles Lineweaver added up the entropy of everything we can see, and found that supermassive black holes are holding more than 99% of it. That ancient light, every photon of the glow that counted the antimatter for us and told us we were 1 in a billion, comes to about 10 to the 89th. The black holes come to 10 to the 104th. The entire fossil record of creation is a rounding error next to what the holes are sitting on. That is where the order goes. Not into you, not into stars, into the things that swallow them. One caveat, and it is a real one. Every word of that assumes the energy of empty space stays exactly where it is. If Deci is right, and that number is drifting, then the whole schedule is wrong, and nobody has any idea what replaces it. The end of the universe is currently an open question for the first time in 27 years. But the direction has never once been in doubt. So line them up, all of them, and look at what you actually are. In the first 30 microseconds, matter and antimatter cancelled almost perfectly. Almost. 1 part in a billion was left over, and everything you have ever seen or touched or loved is made from that remainder. Nobody can say what tipped it. The universe began in a state so orderly that Penrose could only express its improbability as a tower of exponents. And everything ordered has been spending that inheritance ever since: the sun, the stars, the warmth coming off your skin. Nobody can say why it started that way. The ripples it started with sit inside a window about 2 orders of magnitude wide. The only fine-tuning claim that survived inspection, and they are the reason you have a galaxy. Nobody can say why they landed there. The energy of empty space is cancelling to 55 decimal places, right now, or space would have shredded before it made a single atom. The mass of the Higgs is doing the same thing to 32 places, or you would have no chemistry. Nobody can say what is doing either. Notice the shape of that list. Not one of those is a miracle. Nobody has earned the right to that word here. And not one of them is a design either, because when the arguments for design were checked, they came apart in our hands, one after another, with the people who checked them being the same people who had believed them. Every single item is a margin, a gap, a place where the universe was overwhelmingly likely to close the books and did not buy a hair for reasons that are still missing. You are not what the universe made. You are what collected in the places it failed to finish. Which leaves one question standing exactly where Andrei Sakharov left it in 1967. We have not stopped working on it. In an unremarkable building at CERN, machines are running right now that would have been science fiction when the question was asked. In May of this year, the Alpha experiment measured a tiny energy gap inside an antihydrogen atom to 4 parts per million, 100 times better than anyone had managed before, using more than 25,000 trapped atoms of antimatter. They are comparing it, digit by digit, against ordinary hydrogen, hunting for any difference at all. In March, a team drove 92 antiprotons around the CERN site in a truck. That sounds like a joke. It is not. It is the first controlled, reversible transport of antimatter in history, and it exists because the magnetic noise inside the antimatter factory is now the thing limiting the measurement. They need somewhere quieter. And last year, the LHCb experiment saw, for the first time ever, matter and antimatter behaving differently in a baryon. 60 years after the effect was found in other particles, we finally caught it in the family that you are actually built from. Now, the honest part, and it is the reason none of this is a triumph, every one of those results agrees with the theory we already had. Alpha has found no difference. Base has found no difference. The LHCb measurement is exactly what the standard model predicts, and the standard model is still short by 10 orders of magnitude. We have not narrowed the gap by a single digit. What has improved is the precision with which we can describe the silence. 60 years of the finest instruments ever built pointed at the question of why you are here. And the answer is still the same shape it was in 1967. Missing. So, this is where the road stops. And it stops without an answer. Your existence makes no physical sense. That was never a figure of speech. Taken at face value, our finest physics does not require you, does not predict you, and has nothing to say about why the numbers that permit you sit where they sit. Every law we have found bends toward emptiness, toward the even, the cold, the quiet, the finished, and the pool has not stopped. It is in the widening dark between the galaxies. It is in the heat leaving your skin as you sit there. It is in the 4,000 small cancellations going off inside you today. The same reaction that emptied the early universe, still running in your muscles, at a rate you will never feel. You are not a miracle. You are not a design. You are a lean that was never corrected. A rounding error that was allowed to stand and then stood long enough to notice itself, and to build instruments, and to point them back at the thing that almost did not permit it. The universe bends toward emptiness, and it is still, for now, carrying you. Not because you were owed it, because nothing has come to collect.